Information is what we gain when uncertainty is reduced. Measuring it tells us how far messages can be compressed and how efficiently they can be communicated. But we need a way to count that reduction. Suppose you need to travel from London to Scotland by train. You reach the station with minutes to spare, then realise you do not know the platform. It could be any one of 8. The station master knows, but can answer only yes or no. Can you guarantee finding the platform in time? You could ask, is it platform 1? If the answer is no, ask about platform 2, then 3, then 4. In the worst case, you need 7 questions. By then, you may have missed your train. There is a faster way. Ask, is it somewhere between platform 1 and platform 4? Yes, 8 possibilities become 4. Then ask, is it platform 1 or 2? No. 4 possibilities become 2, platform 3 or 4. Finally ask, is it platform 3? No again. Your train must be at platform 4. 3 useful answers took us from 8 possibilities to 4, from 4 to 2, and from 2 to 1. 8, 4, 2, 1. The information is not in the word yes or no by itself. It is in how many live possibilities the answer removes. Each answer removed half of the remaining uncertainty. One such halving gives 1 bit of information. 3 halvings give 3 bits. The platform example hid an assumption. Every platform was treated as equally likely. Now imagine 8 cards. 4 red, 2 blue, 1 green, and 1 gold. Mix them, then draw one. Before I turn it over, which colour would you predict? Red is the sensible guess because half the deck is red. Gold is a long shot because only 1 card in 8 is gold. If the card is red, you would be less surprised. If it is gold, you would be more surprised. Here, surprise is technical, not emotional shock. It means prior improbability. The less likely the outcome was, the more information it carries relative to this deck. Now put numbers to that idea. Red has probability 1/2. Blue has probability 1/4. Green and gold each have probability 1/8. Start from probability 1 and count the halvings. 1 halving takes us from 1 to 1/2. That gives red 1 bit. 2 halvings take us from 1 to 1/2 to 1/4. That gives blue 2 bits. 3 halvings take us from 1 to 1/2 to 1/4 to 1/8. That gives green and gold 3 bits each. The pattern is 1, 2, 3, 3 bits. In symbols, the information in outcome x is minus log base 2 of its probability. I of x equals minus log base 2 of p of x. The logarithm recovers the number of halvings. The minus sign makes that number positive. A certain outcome has probability 1 and carries 0 bits. Before the draw, however, we do not know which colour will appear. So weight each information value by how often it occurs. 1/2 times 1, 1/4 times 2, 1/8 times 3, and 1/8 times 3. What is the average information from one draw? Red appears half the time. 1/2 times 1 gives us 1/2. Blue appears 1/4 of the time. 1/4 times 2 gives us another 1/2. Green and gold each appear 1/8 of the time. 1/8 times 3 gives us 3/8 from each. Add the contributions. 1/2 plus 1/2 plus 3/8 plus 3/8. That is 14/8, or 1.75 bits per draw. No single card carries 1.75 bits. A draw still gives us 1, 2, or 3. Put the card back, shuffle, and draw again. Over many draws, the average approaches 1.75. We can check the same result across the 8 cards. Their information values total 14 bits. 14 divided by 8 is 1.75. Now remove the colours. For every possible outcome, multiply its probability by the information it carries, then add the results. In mathematics, h of x equals the sum over every outcome x of p of x times I of x. We already know that I of x is minus log base 2 of p of x. Substitute that into the average. Entropy is the average information produced by this source. If every color gets a 2-bit label, each card costs 2 bits. Entropy gives us a lower target, 1.75. Can a real code reach it? Give the common colors shorter labels. Red appears half the time, so give it 0. Every other label begins with 1. When the receiver sees 0, it knows the card is red and the label is complete. Blue appears 1/4 of the time. Give it 1, 0. The two rare colors now begin with 1, 1. Add one final bit to tell them apart. Green is 1, 1, 0. Gold is 1, 1, 1. The label lengths are 1, 2, 3, and 3 bits. They match the information values we found for the 4 colors. Variable lengths raise a problem. Where does one label end and the next begin? Test a sequence. Red, blue, gold. Red becomes 0, 1, 0, 1, 1, 1, 0. Remove the spaces. The receiver reads 0, red, then 1, 0, blue, then 1, 1, 1, gold, then 0, red. The exact sequence comes back without separators. This works because no label is the beginning of a longer label. The receiver always knows when a label is complete. This is a prefix code. Now average the label lengths using the color probabilities. 1/2 times 1 plus 1/4 times 2 plus 1/8 times 3 plus 1/8 times 3. 1.75 bits per card. The code reaches the entropy exactly. That exact match works because these probabilities are powers of 2. Their ideal lengths are whole numbers of bits. With less tidy probabilities, a one-card code cannot always land exactly on entropy. Coding longer groups can bring the average closer. The code only used the possible colors and how often each appeared. It never saw what the colors meant. Shannon information answers one question. How much uncertainty did the next symbol remove? It does not tell us whether the message was true, important, or meaningful. Those are different questions.